Okay, I think we did it. All right, folks. Sorry to start a minute late. I was busy sending hay mail to the university, but we're done with that. So today we're going to continue our discussion of vector fields. We've got a bit of kind of a grab bag of topics here. We'll see how far we get, and then we'll continue next time. At this point, since we're kind of in the part of the course with newish material, the timing is a little less clear in terms of integer division of lecture topics into slide decks, but that's okay. I feel like a lot of math classes kind of stop mid-theorem and then have to pick it up the next lecture. Right, so in terms of announcements, your final homework is due tomorrow. Oh my goodness, that is exciting. So the good news is that then you'll be done with homework. For many of the students in the room who I recognize, that's your last homework ever. So that's fantastic. For some of you, it's not, and that's too bad. If you like these homeworks, you can take my class in the fall. I've been just starting to think about homework for that class, and yeah, there's no shortage of really good numerical analysis problems. So those are fun. But in any event, yeah. So your remaining deliverables for this course is one more homework, lots of fun problems, and let's see. It's a whole grab bag of stuff. There's optimal transport in there. There's some differential geometry. So all the good topics. Then beyond that, for the rest of the course, your responsibility is your final project. So please do not view that as like a 2-3 week break and then one more deadline, like the way that you do with your homework. You should make progress on this project at a regular basis to avoid the nightmare scenario the night before when you can't get anything to work. We don't like that. Thea, we need to remember to set up the final presentations.
Okay.
Yeah. So the two of us will work together on that, and we'll share that information ASAP. Any questions, comments, concerns? So quiet. Okay. But it is, it's a Tuesday, so randomly this room has more students than on Thursdays. I do not understand the dynamics of this course. Okay, so right, so then we'll move on to our technical discussion. So today's lecture, we're going to have some mishmash of 3 different lecture topics, which is why I've got all kinds of different notes sitting here, and we'll see how far we get and then just continue next time. So our rough outline here is we're going to try and wrap up our discussion of vector fields today. We may continue this on Thursday a little bit, depending on how far we get with normalizing flows. And then next time we'll talk about optimal transport, and then after that we'll start talking about problems involving shape collections and multiple shapes, so like correspondence, statistical analysis, these kinds of problems. Okay, so that's our sort of broad picture. And essentially we'll just keep going through these topics till we hit the end of the semester, and then we'll stop. So your instructor has far more lecture material than there are days in this course, as you probably noticed, so we can kind of pick and choose a little bit. So, where we last left off, so in our previous lecture, we were talking all about vector fields on manifolds. If you recall the basic story, so a vector field is essentially an assignment of a tangent vector per point on a surface or on a manifold. And that essentially, it's easy enough to define one of these objects, but they're a little bit tricky to work with in differential geometry. Like we talked for almost the entire lecture last time on how to take the derivative of a vector field. The basic story there is that it's complicated. It's not obvious how to set such a thing up. But eventually we arrived at this sort of central object called the covariant derivative, which gives us a lot of the properties that we want and allows us to rewrite things like geodesic equation in very kind of clean notation. So that was our story from before. And then last time I kind of left you with a bit of a puzzle, which is what could I do if I've got a collection of vectors at a point and I want to encode them all up to ordering, at least in the plane. And I thought I'd sketch out a little bit why people care about this sort of problem. There are many reasons why. I think the most concrete one comes up in meshing. So I have a region in the plane. And let's say that, for example, my region is maybe obviously this is a part of a larger picture, but maybe it's like a corner of a rectangular shape with some kind of rounded edge. Right? That's a very typical task. And maybe I have a region like this, and my goal is to fill it with quadrilateral elements. So I want to fill this with little quads. Right? We've talked a lot about triangle meshes in this course, but a different thing that people use a lot in computer graphics is quad meshes, which are useful in simulation and certain other tasks. And so one way that folks will do this is they kind of think about the limit as you make your grid finer and finer and finer, and eventually this thing sort of approaches some object that looks like a vector field. So I thought I would draw you an example of why these problems are kind of annoying. And then we can think a little bit about the right field representation. I struggle to draw these pictures, so we're going to see if I manage. Okay, so let's say that I want to make a quad mesh in this region. And in particular, here's a reasonable one. Hopefully you agree so far that there's quadrilateral elements. But maybe I'm going to insert what we call a singularity point at this location here. Those of you who saw my student Paul give a talk in the graphics lunch a couple days ago, this picture will look very familiar. I'm drawing curves, but obviously you could replace these curves with straight lines. It's just because I'm bad at drawing meshes. But in any event, here's what we're going to do. Now, here's an object which is almost everywhere a quad mesh. Of course, there's one location where it is not, which is here. But in fact, just out of laziness, let's say that I get rid of one of these radial lines. There's a way to fix this. I'm just bad at drawing. Then one thing I could do is the following. It's just erase that one little internal edge. So I've got this object. Obviously, this has some big elements, but if I kind of shifted the edges around, that could fix that problem. Notice that everything here is at least topologically a quad, right? Like even this little thing in the inside has now got 4 sides to it, right? So this is a network of quadrilaterals. They're actually all pretty close to squares. And this is a very typical problem in computer graphics, in quad meshing, where essentially what you want is to fill a region with quadrilateral elements with the property that, especially the quads near the boundary of the domain, sort of one of the 4 faces of your quad aligns to the normal. This is kind of a basic problem. And so this mesh looks innocent enough. It's got one kind of fun, interesting point here, right, in the center. Clearly something is special happening here. I see your hand. And so the question is like, well, what do we do with this object? Like, how do we represent a mesh like this? And in particular, how can we use differential geometry to describe a structure like this, where like maybe our initial inkling might be to like place vectors that kind of point along the mesh edges, but we're going to see that there's a problem with that. Yeah, Matthew.
So the edges that you've drawn, like at the edge of that mesh on that corner, they're not really straight, but like up the rounded corner.
Oh yeah, I mean like in reality, straight. Like I would make them straight lines. Okay. This is just because your instructor is bad. The easiest way to construct one of these singularities is kind of glue a circle onto a L shape, which obviously you could do if you
just have more quads.
That's right. Yeah, absolutely. Right. So we'd like to maybe think about there being like a little vector field which is giving you the directions of these edges. And indeed, a lot of the algorithms that do quad meshing do precisely that. They compute a smooth field, which is kind of guiding the placement of these elements, and then they stick down little squares in like a little tiling fashion. But let's see what goes wrong. So let's say that I have a vector field, and maybe I make 2 of them, like an up field and a field that points to the right. Yeah? Now, here's the basic issue, is let's drag this field around, right? This feels a lot like our construction of optimal, I almost said optimal transport, but that's not right. What am I thinking? Parallel transport. But when we do that in this field, we're going to reach a contradiction, which is a problem. So let's say that I take this little pair of axes. Does everybody see I've drawn one arrow up and one arrow to the right? And now let's drag it to, I don't know, what's our favorite point? How about this guy here? If I had colored chalk, I would use it, but I forgot to bring it to the class today. So we're going to kind of follow 2 paths. One is going to kind of go like down and over, and the other one's going to go kind of around this way. And we're going to see that there's a problem. So let's say that I take this little angle that we're drawing here, and I can shift it around in this region so long as it stays parallel to those 2 directions, right? Then clearly, if I kind of go down and to the right, you know, notice that all of these vectors are just forming a grid, right? So then my directions would be up and right, like that. Does everybody agree with and kind of understand this picture so far? But now, what's going to happen if I take exactly the same frame, and rather than moving it this way, I move it around the circular arc. So now I've got this angle like that, and because it's following the grid, it's going to kind of rotate by 90 degrees. But now what's going to happen? Well, now we're going to have a right and a down. So what does that imply? That implies that like I can't just have 2 fields, like an up field and a right field, and globally kind of have them, you know, use that to represent this thing, this particular structure. At least if I do, it's going to have a discontinuity somewhere. Like I'm going to have to take scissors to this domain and kind of cut it. Does that make sense? And so that's why, essentially, one way to put it is that you can't comb this field. I think that's a really cute term here. I think the computer graphics community actually kind of invented this idea that, like, you know, if I have a field of plus signs, I want to be able to label them like up, down, left, and right, and do that globally. This is not possible globally in this domain. There's an issue. Okay? And so, kind of motivated by this picture here, people said, okay, so great, vector fields are no longer enough. We need an object that we might call a frame field or direction field or whatever, which is going to couple together a set of vectors at a point in a way where they're unordered. There's not like vector 1, vector 2, vector 3, vector 4, but rather it's just like a little plus sign sitting at a point. Does that distinction make sense? Do you see how like this is an example where you can do one and not the other? Yeah?
But don't we get the same issue here if you only look at vector fields? Like, we would also have that discontinuity somewhere, right?
That's not entirely right. I mean, you're right if you talk about unit vector fields, that's true. But if you allow your vector field to kind of have norm 0, at least at an isolated point, you're okay. Yeah. Like, clearly something special also happens at this point. But you kind of hope at least, like, for instance, I could take this domain and just punch a hole in it. Just size that little piece altogether. I just drew a grid, which was not a good thing given the problem we're working on. But I could make it into like a little donut, and this problem would persist, but now the problem you mentioned would go away. Yeah. Okay, so, right. So essentially what we'd like to do is to be able to take, here's some more examples of like direction fields, and like, this is terminology from this survey paper in 2016, where essentially they talk about there being like directions or vector fields depending on whether you like make them spaced evenly or not. Like, can your plus signs, do they have to have an angle 90 degrees? And here's a case where essentially 2D and 3D or higher dimension decouple a lot. Like, it turns out that there's many really beautiful representations for these objects in 2D, and very rarely do they extend beyond 2 dimensions. There's a special reason for that, which is that we can take the tangent plane of our surface at a particular point, and we're going to identify it with a very particular plane, which is really convenient to work with, which is the complex numbers. Okay? So, for example, let's say that I have a vector, and I only care about it up to sign. I want like a vector plus or minus that at every point. So sometimes we call this a line field, right? Now, it wouldn't be so great to have to store 2 vectors at every point. In fact, you can cook up topological examples where they like flip when you go around a loop. But instead, here's the thing that we could do. Let's say that I take my tangent plane and I just identify it with the complex numbers. Like, I just take 2 orthogonal directions in the plane, and I call one of them real axis and one complex. It actually doesn't matter which ones. Now, what could I do? Well, I could take a vector in the complex plane. There it is. And remember, we want to code this thing up to sign, so we also want this one to be there in kind of a democratic fashion. Anybody have any ideas? Like, thinking of these as complex numbers. You can tell they're complex because I wrote the C there. Right, so this is like the real part and the imaginary part. How could I store plus or minus v? Any ideas? There's some really sneaky tricks here. Yeah?
You could also just look at an angle between 0 and pi.
I could do an angle, but then I wouldn't have the magnitude.
Yeah, okay. But you can have a magnitude plus an angle between 0
That's true, yeah. So I could use a polar representation. That's actually one we'll come back to later. Here's the thing we could do. Just store v squared. Right? Because if I know v squared, then I know v up to sign. Does that make sense? Now, what if I want to store 4 orthogonal vectors?
e to the power 4.
That's right. Thanks, doesn't. So that would be v to the 4th. So essentially, here's a kind of sneaky way to store a bunch of vectors, is to say, okay, rather than storing these vectors, I'm instead going to identify the tangent plane with the complex numbers and then store a power of that number instead. Right? Now, that gives us a representation. Computing derivatives of these fields is kind of annoying. You have to kind of go back and think through your derivative formula and see how it commutes with this stuff. Well, I'm going to leave you guys to take a look at this survey for how to do that. But just in terms of representational concerns, there's one case that we haven't considered here. It's kind of a fun one. It's actually relatively underexplored in the literature, which is the following. Let's say that I have 4 vectors, and they're just four vectors. There's not, they're not orthogonal, no nothing. So I have v1 to v4, and I want to store them in some fashion that like remembers all four vectors, but only up to ordering. Does that make sense? That's sort of our goal here. Any ideas? How could I do that? Anybody taken an algebra course? Maybe remember there are actually two equivalent tricks here that we'll sketch out. Yeah.
You could store the polynomial whose roots are the four vectors.
That is a fantastic idea, Karthik. Brilliant. And it was just proposed in literature a couple of year ago. See, this guy, he's ahead of his time. So in particular, let's define a function, f of x. And this is the function, so it like inputs a complex number and outputs a complex number. And here's going to be f of x. It's going to be x minus v1, x minus v2, x minus v3, and x minus v4. Okay? So this takes a complex number and then returns this product of four things. Does everybody understand that this is a thing I could define? Obviously, f is parameterized by these four vectors. Now, why do we care about that? Like the function f has this. What are the roots of f? The v's, right? So somehow, if I know f, then I know the v's. If I know the v's, I know f. The question is, can I store f? But notice that like f, if I somehow had like a black box that just evaluated f, it wouldn't know which root was like v2. It would just know that it's one of them, right? The numbering has been lost. So that feels good. But the question is, how could I represent f in a fashion that forgets the ordering of the v's? So what Karthik is suggesting, which is a fantastic idea, is I'm going to take this product and I'm going to expand it, which is really ugly, and I don't feel like doing it, but we'll do it for a little bit. So what's the first term? It's x to the fourth. That one I'll do. The next one is going to be minus v1 plus v2 plus v3 plus v4 x cubed, like that. Now we've got a plus, and then it's going to end up with like v1, v2 plus v. Do you get a no? v1, v3 plus so on x squared plus v1, v2, v3. Actually, I guess it's a minus x cubed plus v1, v2, v3, v4, x to the fourth. Right? Does everybody agree that there's some form that looks like this when I expand this product? I'm being lazy and not writing the whole formula. Yes, Matthew?
Was there an x to the fourth?
Because I'm wrong. That should be. Thanks, guys. Math is hard. See, this is what happens the second that I don't put things in my notes because I'm confident I can do it. Then yeah. Okay. So modulo the many mistakes that I've already made, I think we're good. Okay. So obviously, obviously, not obviously. I can write an equivalent expression, which is as follows: x to the fourth plus c3x cubed plus c2x squared plus c1x plus c naught, like that, where the c's are just functions of v1, v2, v3, v4. And notice, do these c's care about the ordering of the v's? No. So this object, in the graphics letter at least, is called a polyvector field. And the idea is to basically store a tuple of vectors in an order invariant fashion. And the way that you do that is by kind of making two observations. One is that you identify the tangent plane with the complex numbers. And then the second one is that you can kind of, once you do that, you can define a function whose roots are the numbers you're trying to encode, and then just write down some equivalent representation of that function that doesn't care about ordering. Isn't that sneaky? It's a really fun trick. So if you like this kind of thing, I encourage you guys to take a look. Here's one of the original research papers that was proposed on this topic. Good inspiration for those of you on the faculty market someday. Like, I think Olga basically built her career on this kind of idea, which is cool. Since then, she's done a lot of other cool stuff too. But in any event, this is a really simplistic representation and one that makes perfect sense in this literature. If you have taken an algebra course, you may have recognized and get to essentially exactly the same conclusion in a different fashion. So notice that, like here, v1 plus v2 plus v3 plus v4 is like sort of all of the possible monomials of degree 1 added together, right? This is like all the possible quadratic things added together, cubic and so on. So these things are polynomials in the V's, these coefficients. Does anybody happen to know the names? It's a good trivia question. These are called these symmetric polynomials. So if you Google, this is like sort of algebra's way of encoding sets of complex numbers up to ordering. Now, you might ask, can I do the same thing for collections of vectors that aren't in R2? Because now I don't have the complex plane. And the answer is, we don't know. The obvious ways of extending this don't really carry through, right? From step 0, like I needed complex numbers to do this. So even just like taking the analogy of this story in 3D is extremely complicated. It's not so clean. And so there's some really interesting representational questions hiding in this domain. Yes?
What goes wrong if you try using quaternions?
You can. So quaternions are commutative, for one. So you'll end up with multiple representations of the same tuple. Yeah, depending on like the order of this product. Yeah. Right, like commutativity actually mattered here, right? We kind of commuted all these products. Yeah, it's really subtle, right? This stuff is funny. I think there have been some attempts to do in quaternion space, but there's like some engineering that has to happen. Yeah. Okay, fantastic. So that concludes, that's just our little last stub of discussion from our previous lecture on vector field theory, the one little last thing I wanted to present you with, because it is an example of a pretty tangible open-ish problem that people still study today, which is just taking any of this two-dimensional story and making it work in like 3D. I think it's a very, very concrete thing to think about in the shower, like just like really annoying algebra question. If you like this kind of thing, I included slides in the slide deck on some progress on this problem because it happens to be one that I care about. But we're going to skip that for now and jump right to discretization stuff. You'll notice from those slides that there's like a lot of ugly algebra notation. I'm not touching my laptop and it's still changing the slides. Ta-da! Okay, so our next topic of discussion, continuing the usual boring structure that we have in 68410 here, is now that we've covered a little bit of the smooth theory and at least kind of hinted at why smooth vector fields are so annoying. We can talk about how they're annoying in the discrete case as well. Now this is, again, if you like this kind of topic, this is a topic that people build their entire careers on, like just representing and working with two-dimensional vector fields on triangle meshes. It's just like a thing many people study in computer graphics community. So we had the luxury of like roughly 30 minutes to cover this giant topic. And so roughly what we're going to do is give you just an idea of the kind of approaches that show up in this space so you can at least understand why they're hard. And the kind of interesting thing here is these are really recent. Like, a lot of the things we covered in this course are like 90s and early 2000s in terms of geometry. This is like the last 5-10 years that people study these problems and think about them in a really mature way. So if we kind of return to our previous lecture, remember we talked a little bit about some of these challenges in the theory of vector fields. Now we can ask questions involving representation. So like, what does it mean to store a vector field on a surface is the first question we should answer. And then from there, how might we take derivatives of these objects, find their singularities, compute flow lines? These are all difficult tasks that are both annoying to implement and to write theory down for. Right? So this universe of discrete differential geometry is quite challenging in this domain. And unlike in some of the lectures in this course, so for example, if I ask you to compute Gauss curvature on a triangle mesh, I would say most people in geometry processing community would probably sketch out roughly what we did in this course. Like they compute angle deficit, maybe divide by the barycentric area, and we'd be done. In this area, there isn't consensus. That there are many different representations, and lots of people have proposed different representations that work in different application domains. And it's not clear how well this picture commutes. Like, can you kind of choose one application and one vector field representation, or do they somehow go together in some intricate fashion? This is a messy space, and there's still room for improvement and innovation, for sure. And of course, vector fields show up in so many different communities. That's part of the reason why there isn't consensus, right? Like, we'll talk about a very geometry processing kind of intensive approach to this space, but of course, vector fields also show up in simulation. They show up in any dynamical system, and each one of these communities has their own kind of approach to these problems, for arguably no real good reason. But that's a different story. Okay, so just like many lectures in this course, we are encountered with PIG, and our goal is to cover it in hair. So we need some different representations for placing those tangent vectors on this object, and then working with, for example, the derivatives that we defined in the previous lecture. And notice that already that feels difficult, right? Because in this course, we've talked a lot about finite elements, but vector fields already kind of feel like the first derivative of something, right? Like a scalar function, maybe. And if we do a piecewise constant finite element, we have no hope of differentiation. So like somehow we're hosed from the start. So we'll talk very briefly about three different vector field representations. We're going to focus on 1 and 3, and we might come back to 2 depending on whether students in this course are excited about exterior calculus or not. We'll have a grab bag of different topics toward the end of this class that we can choose from. Right, so we'll start by talking about triangle-based vector fields, because I think these are the most tangible, and also I think the sort of default option for a lot of people in this community, which makes good sense, right? In fact, we've already encountered triangle-based vector fields. Do you guys remember this? So we had scalar functions on triangle meshes, right? And that's just like one value per vertex of the mesh. And we talked about this piecewise linear finite element model, right? The idea that if I have one value per vertex of my mesh, then, for example, when I take the gradient, right? Remember how we constructed that? We got one vector per triangle, where we kind of linearly interpolated that function along each triangle face and then took the gradient. Does that story sound familiar? No? I hope. Yeah. Right, and so that was our sort of first example of a vector field, right? It's a perfectly well-defined object. And of course, the nice thing is that triangles have tangent planes, right? Triangles sort of arguably are their own tangent plane. And so it's very clear what two-dimensional basis to use here. And so I think the model here for a triangle-based vector field is extremely simple. We just have one vector per triangle, and we really view this as a piecewise constant object. Right? So like our functions were kind of linear, right? They interpolated values on vertices. Here we can think of vector fields as just one constant throughout the entire triangle. Of course, that creates some challenges, because when you traverse an edge, your vector field changes discontinuously. Right? On the other hand, certain things are much simpler to define in this regime. So if you recall, last time we talked a little bit, we suggested this idea of a connection, which is a means of essentially comparing tangent vector fields or tangent vectors to one another. And I would argue that connections are actually much easier to understand in the discrete case than they are in the smooth case. This is a sort of happy benefit here. So in particular, let's say that I want some notion of parallel transport. In some sense, there's only one notion that I think, if I ask you guys to like move vectors around from one triangle to its neighbor, that I think you could cook up with, that really feels kind of twist-free, because remember, that's what parallel transport is. And so this is illustrated on the slide in the lower right here. So let's say that I have two triangles that share an edge, and both of them have, you have a tangent vector on one, you're trying to translate to a tangent vector on the other, like this blue guy. So here's the basic procedure. You take this edge here, and you just kind of unfold it. And when you unfold this, of course, this is something you do mathematically, right? This is just a construction to kind of help you visualize what the parallel transport is doing. But essentially, when you unfold an edge like this, there's a rigid motion that undergoes, so it's very clear what happens to the two tangent planes, right? Like it's just rotating about that shared edge. Now, once you've unfolded to something flat, it makes perfect sense to displace your vector. You just slide it along the plane without doing any parallel transport at all. And then once you do that, now you can compare. You can fold it back. Okay. And so this is the notion, the discrete notion of discrete. The discrete notion of discrete parallel transport that I think most of this community agrees on. So if this, the fancy phrase for this is that this is the discrete Levi-Civita connection. Remember, a connection gives you a means of comparing tangent vector fields. And remember the sort of notation here that like a connection is like, grad W in the V direction. So at least here we can take connection in the direction of the shared edge, or maybe orthogonal to it, of the field which is piecewise constant. That makes sense? So you sort of get three connection values per triangle. More generically, if you have a connection which is not the Levi-Civita connection, one way that you can express that is to attach a little angle on every edge. So you say, I'm going to do the Levi-Civita connection, and I'm going to rotate clockwise by 10 degrees, right? And so if I store an angle on every single oriented edge, it needs to be oriented because I need to know which direction is clockwise, then what I get is just a discrete connection more broadly. Does that make sense? Okay, so that's our basic terminology here. Notice that there is a notion of holonomy here, and in fact, in your homework, you showed that this is another way to get Gaussian curvature, right? Because in particular, if I have a folded up vertex, if I fold it up here, I just mean a vertex with curvature. Right. Chuck. So let's say that I have a positively curved vertex here. Right, so it's got maybe edges, maybe it's a tetrahedron, like that. Right, this has positive Gauss curvature. Hopefully we all agree on that. So if I took my little pair of scissors, like that, those are scissors in case you're wondering, and I cut along this edge, and I lay out those triangles, what would I get? I would get, like triangle 1, triangle 2, triangle 3, something like that, right? And then this angle here is in some sense the curvature, right? So notice once I do that, like basically I've just unfolded these triangles. So if I take a vector here, I can now do my parallel transport, right? So like this would say, I draw a vector on this triangle, or I guess two vectors here, then it gives me means of moving it to the next triangle, just by displacement in the plane, and so on. And now, remember what holonomy is doing. It's saying like if I parallel transport something in a loop, I don't end up where I started. And notice that that's exactly what's going to happen here. Because now, let's say I want to parallel transport this guy back, right? One way that I could do that would be now to take my scissors to this shared edge, take this triangle and kind of move it around there to this side. But I have to move the vector along with it, right? So it's going to rotate by this angle. So now my thing is going to point like, oh God, kind of down, and this is like that. Spatial reasoning is really hard. And notice that these two things are no longer at the same angle. They flipped. I think I managed to do that right. And this is, again, just by taking this L and kind of moving it around that loop. Thank you, Anna, just like that. Yeah. Okay, so, right, so that's our notion of curvature, and I believe on the homework you actually showed that this is precisely the same as our discrete Gauss curvature that we defined in class. Yeah? So that's kind of fun. We have some notion of structure preservation, which is great. And then again, like we mentioned before, a more generic kind of arbitrary connection that isn't the Levi-Civita connection we can specify by just adding an angle of rotation that you undergo when you pass through this edge. So you like pass by translating, and it's like, you play Monopoly, like do not pass go, rotate by 10 degrees, and go to the next triangle. Okay? So that's our basic technique. Notice that like holonomy around a vertex, it has to add up to Gaussian curvature, right? And so there's some constraint on the set of rotation angles here. Does this make sense? Let's think about it for a second. So in particular, when I go back around the loop, like that defines the Gaussian curvature of my vertex, right? And we know that we integrate Gaussian curvature over the whole surface. Remember this theorem? I get a topological invariant, right? So I can't arbitrarily make a connection by just like randomly drawing an angle on every edge independently, IID. They need to sum up to a particular value, right? They need to sum up to like the Euler characteristic. That's 2 pi. Okay? But that observation alone already led to a very popular algorithm for vector field design on triangle meshes. This was something called trivial connections. Amazingly, this was proposed in 2010, which was like the Middle Ages for you people. I think Dustin wasn't even alive. And essentially, this was one means of designing a smooth vector field. And here's the basic intuition. Let's say that I want to design a vector field. I want to like put a little arrow at every point on a surface, and I want that to be a smooth function, right? And so maybe the best way that I could do that would be to imitate the connection as closely, the Levi-Civita connection as closely as possible. So what I would really love to be able to do is to stick a vector on one triangle of my mesh, and then just parallel transport it everywhere else. Like, if I have that vector on, this triangle here, here's my vector, then maybe I just do parallel transport to move it to its shared edge. And you can imagine a universe where I literally just compute a tree, like a spanning tree of the triangles, and then just do parallel transport along all those paths. That's a reasonable starting point. But of course, the problem is if I did a different spanning tree, thanks to holonomy, I'd get a different vector field, right? Hopefully we all agree. We're not like these. I'm using a lot of math terms and I'm using them quickly because you guys are all smart and we've used them a lot now. Okay. So this is an algorithm for trying to cope with that in a better fashion, right? So that's the basic trick. And so here's what they're going to do. They'll say, okay, the Levy-CVT connection doesn't quite work here. We can't just do parallel transport because around loops, something goes wrong. So instead, what we're going to do is we're going to design a connection. Like we're going to put an angle on every edge so that things do kind of add up into the right kind of loops. This is kind of clever. And moreover, we're going to make it basically zero everywhere that we can, except when we can't. So like we can take big swaths of triangles and at least conceptually lay them out on the plane in a flat fashion and do a flat connection. It's just every once in a while we're going to have these singularity points about which the field is circulating. So one way to understand this is kind of taking all the Gaussian curvature of the entire surface and then just concentrating it at a few isolated locations. Okay, that's sort of what's going on. And so here's some details of the algorithm here. And I encourage you guys to read this paper because it's kind of interesting historically. Like it's one of the earlier vector field design papers, and so it like doesn't use quite as sophisticated language for describing some of the stuff than appeared in the later papers, which are much harder to read. It was actually kind of mostly just a discrete thing that they designed at the time. In fact, actually, Fernando de Goes, who's now at Pixar, wrote a little document that he released that kind of went through how you could interpret this algorithm in differential geometry. But the original one was not. It was just discrete, like a little combinatorial thing on mesh edges. But in any event, the basic variable here is this thing they call theta edge for like this sort of excess rotation on every edge of your mesh. And then they say, okay, we're going to take a bunch of basis cycles which are going to have basically no holonomy. So I'm going to try and design theta so that around most vertices, when I go around a loop, I end up back where I started, right? And then just on a few isolated places, I'm going to fix the curvature, but maybe I do it in a really clever way that's like a multiple of 2 pi, so that like, yeah, I loop around, but I always loop back to where I started, right? And so they set up a linear system. They say, okay, well, this is an underdetermined system. So now I'm just going to minimize the norm of this thing. And what comes out is a connection. And now I just specify a vector on a single triangle of my mesh. And magically, because I have designed a holonomy which is constrained to be flat at most vertices, I can now do this spanning tree procedure and it works out. I get something smooth. Really sneaky. A really interesting question, which is really hard to think about, is, so this is like a sum over the mesh edges of the squared holonomy angle. If you're a differential geometry student or like a future student of the author of this paper, you might think about what does this thing correspond to in the smooth case? Like what is this integral? And it's really not obvious, I think. Okay, so even if we don't follow the details of this paper, we can take a look at pretty pictures. So here's what interacting with this algorithm looks like. You place a few singular points for your field. So these are the places where the holonomy is not constrained to add up to 0 when you go around the loop, but rather will be constrained to add up to some other like integer multiple 2 pi. And you have to be a little careful to make sure that these guys' indices add up to the Euler characteristic of the surface, right? Because otherwise this doesn't work. But in any event, you do that, you constrain these things, you solve, and then literally you just kind of define a vector on a single triangle and then just propagate it everywhere else. You get a nice smooth field. You have to be a little bit careful. So we asked earlier, I forget who, somebody asked about like a polar representation. Notice that that's in effect what's going on in this algorithm, that like the norm of the vector field doesn't change as you move it around in this connection. It's just a bunch of angles. That's good and it's bad, right? Like the good thing is it doesn't like vanish in some weird fashion. There's no cancellation that happens. On the other hand, this is not a smooth vector field in the sense that at these singular points, it's got like unit norm as you zoom closer and closer to the singular point. So it's like cycling infinitely fast. So this is something that works in the polar domain. Any questions? This is kind of a fun paper to read. If you're looking for a good one for your reading assignment this week, this would be a nice choice. Yeah.
Wait, can we also see the other side of the bunny? Like,
no.
It looks always smooth there.
Yeah, it's an interesting question. I wonder. It's funny. I mean, this figure is just borrowed from the paper. I'm assuming that the authors didn't have any ill intent here. They're just trying to demonstrate the smoothness. But probably around these points, it's like circulating or pointing in or making like a little hyperbolic shape or whatever. This is a reliable algorithm, and it's implemented in many geometry processing toolkits. Yeah. Any other questions? That's funny. I never really thought about it, but you're right. This is a figure we all borrow. I don't know. One fun question you might ask is like, can I make this algorithm work if I have like triangle soup, where I start punching holes in this mesh? And the answer is, it gets a little complicated. Yeah.
You brought up a few times that hairs on animals that can be treated as like vector fields.
Yeah, it's a sore topic for me.
But like, is there any intuition like so? Because I guess like on the head we can also see this singularity point.
Mm-hmm.
Like, is there any notion of like which particular parallel transport is used like in nature?
What notion of parallel transport is used in nature to design the vector field of your hair on your head?
Yes.
That is a fantastic question. I haven't the slightest idea of the answer. Yeah. There's another one. I know that like fingerprint people is another one that they think about a lot, right? Like if you look at those like CSI things, they have this classification of different fingerprints, and you can totally approach it with this language. Like there's different singular points, different ways it circulates around. But I am not an expert. No. I encourage you to look. In fact, use that for your reading assignment. Find something about hair follicle stuff. Then tell me what I did wrong. Yeah. Any other questions here? Of course, the reality with hair is that it also tends to not be padded flat on your head unless you're like, 1920s mobster type. And so probably this is not the end of the story, right? There's a normal component as well. Yeah. Okay, so so this is our first example of a vector field design algorithm. And the good news is that it's relatively simple to implement. It's a little tricky to understand in differential geometry language or like PDE language. And so a lot of people have made some effort beyond this research to kind of design different techniques that are a little better interpretable in the smooth case. But the good news is that like sort of from a discrete differential geometry perspective, it's really clean, and it deals with like some preserved structure here, right? Like there's some nice topology going on with the vector field, making sure the singularities add up to the right indices and so on. There's different structures that you can preserve in your vector field decomposition. You notice, by the way, I'm stealing a lot of slides from my colleague Kim because he works on these topics a lot. Our next lecture is in optimal transport, and then those will be mostly stolen from my paper. Temperature warning. This keeps happening. It's too hot, these vector fields. Okay, so in general, if I have a vector field, this is something you probably don't remember from your calculus class, but I'm guessing you actually did cover. There exists something called the Helmholtz-Hodge decomposition, or I think we're often lazy and just call it the Hodge decomposition of your field. I think you often see this in like just the 2D plane, but the same thing exists more generically, and it says the following. I can take any smooth field on my surface, and I can decompose it as the sum of three objects: a divergence-free field, a curl-free field, and a harmonic field. Now, roughly, what's going on here? Curl-free fields are ones that are just gradients of functions. Right? These are fields that kind of don't circulate at all. Because remember, what is curl of grad of function, at least on the plane? Zero. Which makes sense given the name. There's divergence-free fields. These are the ones that just purely circulate. And one way to represent these is actually to take a curl-free field and just rotate it 90 degrees in the tangent plane. You can kind of see that like you could obtain something that like points out for the singular points here by just rotating everything a little bit. And then there's a third one. This is specific to geometry, where if I'm on a smooth surface and I have a 2G dimensional space, these are both infinite dimensional, right? They're like functions. We have a third one, which is a finite dimensional space of what we call harmonic functions, or harmonic vector fields, which are things that like circulate around the outside of a donut, right? So for every like kind of topological generator, like a loop like this, I get a field that kind of follows around that. And there's two, like for example, in the donut here, there's one that goes this way and another one that kind of cycles around the donut. We do a lot of like gestures today. Okay, so one question you might ask is whether you can kind of take this picture and make it work in the discrete case. Right, so in particular, we have the space of all possible vector fields, which at least for this little chunk of lecture, we might think of as just one vector per triangle face. And the question is, can we derive a discrete Hodge decomposition in the same fashion that we've done here? And we have the tiniest bit of a clue, which is at the very least, we know how to do gradients. Right? So we know we have some little subspace of that 2T dimensional space that we know how to deal with. That make sense? And this was a question that was asked many times. I think one of the first times that I saw that was really clean is in the PhD thesis of somebody named Max Wardetsky. This is a name that shows up a lot in this domain. But essentially, if we say, okay, we have sort of two pieces, we have the space of all vector fields, we have the space of curl-free fields, how can we get the other two? Or maybe we just focus on the one on the left, and the harmonic piece is what's left. Okay, so if you recall, we actually talked about how we can get gradient fields on triangle meshes. I think this is old news. And moreover, we have one additional fun fact about triangle mesh. We're going to only assume there's no boundary for today, because math is annoying when you have boundaries for your vector fields. Which is that we have this topological invariant, v minus e plus f is equal to chi, which is 2 minus 2 times the genus, where genus is the number of holes. Okay. So here's a kind of funny little calculation we could do kind of speculatively in a funny fashion, which is just like dimension counting. Like essentially, we know some dimensions. Like for example, if I have f triangles, remember f stands for faces, then what's my space of triangle-based vector fields? What's the dimensionality of that? What was that?
3F.
Almost, but we don't have a normal direction.
2F.
2f, that's right, right? You have sort of two directions per triangle tangent plane. And so one question you might ask is the following. Let's say, if we go back to our hot decomposition here, so we kind of know what our space of gradient fields is going to look like. We're going to assume that there's some 2G dimensional space of harmonic stuff out there. Then we might ask, well, what is the dimensionality of the divergence-free fields, and does it make any sense? Right? We can just do some counting here. So let's do that. This is a fun little accounting thing, and it actually, I think this is, I don't know this story, but I believe this is where this research comes from. That like literally people did degree of freedom counting, stepped back 10 feet, and then thought like, oh, maybe we should have this other representation of vector fields. Oh no, I gave it away. Okay, so our dimensionality here. Let's do some dimension counting. Okay, so we have a face-based vector field, and we're going to represent this thing. This is a 2f dimensional space. Hopefully, do we all agree now that this is right? Cool. And we have curl-free fields. Remember, those are like gradient of the function. What's the dimensionality of this? So like how many values does it take to specify f in our model here? 1. No, there's definitely more than 1 degree of freedom. Yeah, like if I have a function on a triangle mesh, remember we started with like 1 number per vertex? You guys are looking at me like I'm speaking in like Swahili right now.
V minus 1.
V minus 1. That's right. So we have 1 number per vertex, right? Yes? Some acknowledgement? Oh my god, you're killing me. Yes? Okay. And if I take my function and I just shift it by a constant, what happens to its gradient? It's the same? Thank you. I know like our Tim knew it, but he wasn't going to say it. So that's why I have v minus 1. I have to remove the space of constant functions because they don't affect gradients. Everybody with me so far? You're like even more brain dead looking than you normally are. Okay. So let's do a little bit of math. So we have 2f is the dimensionality of the space of face vector fields. And now remember that v minus e plus f is equal to the Euler characteristic. So secretly, I can write a really weird expression for this. This is 2 times chi plus e minus v. Did I do that right? I did, yeah. Okay, and moreover, let's put the genus in for chi here. Okay, so this is really 2, and now it's 2 minus 2g plus e minus v. Okay? All right, so if we expand this out a little bit, what are we going to get? We will get that this is 4 minus 4g plus 2e minus 2v, like that. Okay. And now, remember our goal here. So our goal, we're looking at the Helmholtz-Hodge decomposition here. And we have these 3 pieces, and we're trying to kind of count the dimensionality of the divergence-free fields. That's what we're aiming for. Okay. So here's one way we can kind of cheat when we do that. So we already know the dimensionality of the curl-free fields is v minus 1. And we know the dimensionality of the harmonic fields is 2g, like that. So maybe here's the thing that I could do. I could say this is equal to 2g plus v minus 1, and then just kind of subtract off these two things from this expression here, right? Like this is like one of these cases where you're doing a calculation because you kind of know where you're headed. And so in particular, I will get, you guys are going to verify that I did this right, 5 minus 6g minus 3v plus 2e. Do we all agree here? Because we've got 6g, because you've got a 2 and a minus 4, so you get a minus 6. Similarly, you have this is a minus, in case you're wondering. The minus 1, you got a 4, so that makes a 5, and so on. Cool? Anything? Nods? Yes, thank you. Okay, so, right. So let's apply Euler's formula again. So we know 3 times the Euler characteristic is going to be 6 minus 6g, which looks an awful lot like that, right? And that's going to be what? That'll be 3v minus 3e plus 3f, right? So I just took the Euler formula and multiplied it by 3. Okay? So when I do that, what do I get? I get 2g plus v minus 1 plus, and now let's see here. We have 5 minus 6g, so we want to do 6 minus 6g. Yeah? So we have minus 1 plus this thing. So it's going to be plus 3v minus 3e plus 3f. And then we need these two terms here, minus 3v plus 2e. You having fun yet? I'm having fun. So, minus 3v and a plus 3v, so those go away. That's kind of nice. We have a minus 3e and a plus 2e. Yeah, so let's clean up a little bit. So this is 2g plus v minus 1 plus, we got a minus 1 here. We have a minus 3 plus 2, so minus e plus 3f. Like that. This is starting to look clean. Yeah? Okay, so can we do better than this? Marcel says no. All right, we're done for the day. So remember we had this little suggestive picture. That's probably not a phrase I should use. This image like that. And let's say that I have an edge. So an edge is adjacent to how many triangles, assuming there's no boundary? 2. A triangle has how many edges? 3. So in general, what do we have here? We have that 3 times the number of faces is equal to 2 times the number of edges. Remember this little expression from before? So Marcel, can we do better than this expression?
Yes.
Heck yeah. So in particular, we can get rid of the f term here. Right? So 3f is 2e. So really, this is e minus 1. Did I do that right? I did. Yeah. Oh no, but plus all the other stuff. Sorry. I got excited. So there's a 2g plus v minus 1 plus e minus 1. Like that. Okay, now we're good. Yeah? Isn't this neat? So what did we do? We took, this is just degree of freedom counting. We haven't actually done vector fields yet, right? But we started with 2f, and remember, this is the dimensionality of the space of all possible vector fields if we make them one vector per tangent plane, right? And now we just munged a bunch of topological formulas together. Like this is just algebra. And what do we get? Well, we got the sum of 3 terms. So v minus 1 is the dimensionality of all the gradient fields. 2g is the dimensionality of all the harmonic fields. And then somehow we got something weird. You said we got e minus 1. And that doesn't jive with our initial kind of intuition, right? Because if we go back to this picture we have on the board here, like we have curl-free fields, our gradients of functions. Divergence-free fields are rotated gradients of functions. So somehow, like the representation that might come to mind would be you just take your v minus 1 dimensional space of scalar functions, and then you just literally you take their gradients and you rotate them 90 degrees. which is actually perfectly fine. One of my research papers does this, and I got yelled at by a colleague of mine for making this mistake. But we could do that, or we could try to make something that actually preserves this topological structure. But in that case, what do we need? We need an E-1 dimensional space of divergence-free fields, which is kind of weird. Yeah? And this is actually the first time we'll encounter it in this class, a really interesting phenomenon that happens a lot. This is called non-conforming elements, which is the following. We've done finite elements to like make our functions and gradients. We're going to use a different finite element space to make functions whose gradients we rotate 90 degrees. This is actually common practice in the geometry domain, and in some sense it's like a hack to make all of these dimensionalities work out. But also what people have found empirically is that when you do that, you tend to get a better representation of functions on your surface. And that sort of makes sense, because otherwise, what's going to happen? So in general, there are fewer vertices than there are edges. So somehow, if you represented a field by doing v-1 and then another v-1 by using this picture, then you're somehow missing out on some piece of this space, which is just wrong. We can't have that. So in particular, here's our way out of this problem. So we'll write a little bit on the board, and then we'll go to the slides here. So essentially, what the kind of hint we have here is that we want to store scalar functions, right? Because it's E-1. So like this f here, using one number per edge. Yeah, and so here's the picture that we end up drawing. It's something like this. We've got two triangles that share an edge like that. And now I'm going to think of my function as associated to the midpoint of every edge, like that. If I do that, I can still linearly interpolate these three values to the interior of this triangle. I can use barycentric coordinates perfectly fine, right? Like one thing I could do would be like inscribe a little triangle like that, and say like, okay, well I could certainly do barycentric interpolation in this little inscribed triangle. I can basically just, what's the word I'm looking for? Extrapolate to the remainder of the bigger guy by using linearity. It's just that the weighting is going to be negative, right? I could have negative numbers. Moreover, you get a kind of a funny universe where along this edge, those two functions don't have to agree. This is called non-conforming elements. We'll see a picture of it in just a moment. And this is the way that many people store vector fields. So here's the basic accounting that we just did. And there's basically two different options. We can either store vertex-based gradients and edge-based rotated gradients. That's like kind of what I suggested here, right? And notice that when I take the gradient of this thing that's specified with one value per edge, that I still will get one vector per triangle. It still works out. Hopefully you see that. Or I could do the opposite of that, by the way. I could rotate the vertex-based gradient and keep the edge-based ones as edge. Either of those is fine. So let's see a picture of what this looks like, because it's super weird. Ah, yes, Artem.
So does it mean that we kind of like get this extra degrees of freedom by the expense of allowing discontinuities on the edges?
That's 100% right. That is a beautiful way to put it. You get extra degrees of freedom by allowing for discontinuity along the edges of your scalar field. Yeah. So here's a picture of what this looks like. They're really hard to draw pictures of for precisely this reason, which is this discontinuous on edges. So here are vertex-based fields. This is sometimes called conforming finite elements. You have this nice hat basis functions that we all know and love. Now the basis function for finite element that gets used for the edge-based scalar functions, remember it's one value per midpoint. So it looks like this really weird picture where like they agree on this shared midpoint, but then away from that they actually probably don't. And for whatever reason, it turns out, like God made triangle meshes a particular fashion that obeys this interesting kind of degree of freedom relationship, which is this is the proper way so that you really do get the Helmholtz-Hodge decomposition that you might want. Incidentally, if you use this basis, so this gives you a basis for curl-free, or divergence-free fields, rather. If you wanted a basis for harmonic fields, what could you do? Well, you could just project out these two things, and whatever you're left with is guaranteed to be your basis. Right? In fact, that's common practice here. If you're curious, if you want the sort of analogy of a hat function, I'll give you the expression here on the slide. You can get it. I mean, obviously, if you have the linear function on a triangle, you can get the basis on an edge. You just have to kind of like reshuffle the linear things so the indices work out. But I'll let you think about that at home. So anyway, this is a thing that I think happens a lot in this domain. You do like some degree of freedom counting, and then you kind of stand back 10 feet and you say like, wait a second, so if we want to be able to cover the entire 2f dimensional space of fields, then I need to do something kind of funny to my scalar functions to make this work out. And then you go back and reverse engineer your representation. I think it's a very common argument and something people do. If you go back to our finite element lecture, it's actually perfectly fine to like define Laplacians this way and so on. Like all those integrals we did are perfectly well defined in this space. It's just a different one. It's also kind of nice because the e-dimensional space of non-conforming functions has just got more degrees of freedom. There are more edges than there are vertices on a mesh, which sometimes is kind of useful. So for example, there's a cloth simulation paper from Bridson a very long time ago. I say a long time ago because it was when I was in college, so it has to be a long time ago. Where they did cloth simulation, and they proposed using these non-conforming elements, not because of this degree freedom counting, but just because otherwise cloth locks up. So in particular, like they want rigidity, like cloth, if it's inextensible, there's a lot of bending and not a whole lot of stretching. But there's a problem, which is if you build cloth in the sort of conforming elements and maybe you force every edge to remain rigid, then oftentimes what'll happen is the whole thing, it's what they call locking in physical simulation. It just doesn't, the whole thing locks up. But it turns out over here, if you add the constraints the right way, there's still some nice kind of degrees of freedom because these triangles are allowed to kind of hinge about that shared point. This is a clever trick. I don't know how often that particular strategy for cloth gets used, but it was a nice idea. It was also back in the day when SIGGRAPH papers could be like 3 pages. He just like said, okay, do this, and then tested it, and that was the end. Very different universe. But in any event, it's another kind of interesting paper to read. Yeah. Okay, so if you're curious, you want a 3D version of this story. This one actually does exist, but it's actually very recent. I believe this is SIGGRAPH Asia like 2-3 years ago, where they worked through exactly the same kind of argument for volumetric fields. So the first thing you have to do is go back and find the analogy of the Hodge formula for things in 3D, which turns out to be remarkably complicated when you have a boundary with a region in 3D with a boundary. It's the sum of 1, 2, 3, 4, 5 different terms, and they work through really, really carefully to do all the degree of freedom counting to account for the space of fields, which in this case is like 1 3-vector per tetrahedron. I'm giving you guys lots of pointers into the literature. This is another good one to read for your homework this week, if you have a lot of time on your hands. Okay, so that concludes our discussion of phase-space fields, and I think this is like actually a really elegant space. Like this is a very clean idea, and it's kind of surprising because these fields we think of as smooth objects. Like we're drawing pictures like this nice cat here, but these are piecewise constant. Like differentiating these things is tricky to think about. We're going to defer on edge-based fields. We saw that a little bit with non-conforming elements, and indeed one of the ways that we represent that is using an object called a Whitney form, which really is sort of the dot product of your field with each edge of your triangle mesh, and then interpolating that to the interior of your triangle. I'll encourage you to Google that phrase. And that's best discussed in the context of something called discrete exterior calculus, which is sort of a way of dealing with differential forms on triangle meshes. In some offerings of this course, we've covered it. In some offerings, we haven't. It's a topic that our graphic students tend to want to cover because it's very popular. On the other hand, really deeply understanding it requires a lot of lecture material on construction, so I can never decide whether it's worth it in this class. But if you come to my office hours, we can discuss whether or not to do it, which is basically me just being desperate for you to come to my office hours. Okay, but we are going to skip a little bit to vertex-based field representations, just because these are actually quite common and popular, but they're also quite hard to work with, which is funny. The main basic issue here is that a vertex doesn't necessarily have a well-defined tangent plane, right? I mean, you can get one. For example, a lot of triangle meshes are oriented. They just come with a normal per vertex. But a priori, there's no sort of canonical choice. And moreover, like if you want to do parallel transport, like we did this nice unhinging construction, it's really not obvious how to do it here. Right? On your homework, I think you had one kind of version of this story, and indeed, you really had to think it through, and it wasn't obvious that it was a canonical choice. So the pros here is that like there tend to be some possibility of being able to take more than one derivative of these fields, because somehow there's so much going on here anyway that you're like kind of over smoothing in this view of the universe. On the other hand, there's no natural tangent space, and Gaussian curvature, like oftentimes we're taking integrals around loops to get Gaussian curvature, but our Gaussian curvature tends to live on vertices, so we can't really do that anymore. So this whole picture is just a little more complicated. There is one exception to this rule, which is for flat meshes. Then it's perfectly reasonable to store your vector field as one vector per triangle, or per vertex rather, and just to interpolate the x and y components linearly along the inside of the triangle, right? Notice that like we can't do that on a curved mesh, but you could at least, I mean you can, but like there's no obvious tangent plane when you move through your triangle, so that picture gets a little murky. But for example, in simulation, this is a perfectly fine representation of a field. And moreover, there are a lot of problems with geometry that are really interesting, even though they're flat. Any physical simulation problem involving a Tet mesh is a good example. And there's some in geometry processing. So like, for instance, we briefly mentioned in our previous lecture this idea of a killing vector field, which is like the velocity of a rotation. So killing vector fields, if you define them, they're vector fields whose Jacobians are anti-symmetric. So think about, I think the canonical version of this is like, let's say that I'm rotating about the plane. So I've got a vector field whose traces look like that, roughly. Remember what this field looks like? It's like minus y comma x, something like that. So what is the Jacobian of this thing? Well, notice that the x component only has a derivative in y, and the y component only has a derivative in x. So it's like got this kind of like 0, -1, 1, 0 kind of structure to it. And it turns out that's not a mistake. They're just generically fields that are velocities of rotations and translations have this property. And so there's a whole series of research papers, including some of my own, that essentially say, okay, I can measure how close I am to a rotation by taking that Jacobian and just adding it to its transpose and squaring, right? In this case, I need a Jacobian, so I would like to be able to do like piecewise linear finite elements, right? I want to take the gradient of my field. And so in this particular case, it makes sense to store the field of vertices and then to have a Jacobian per triangle just using the same piecewise linear FEM that we've already done. Everything else in this paper you guys could reconstruct in this class, like having with the material we've already done. But if we have a curved surface, then we can't do that anymore. It's like not obvious how to do that interpolation because you have 3 different tangent planes, and now you can't just kind of average those vectors together and expect them to have a well-defined space, right? And so in this particular setting, there is engineering people do, but there's no sort of canonical decision. So for example, one of the early research papers, actually it's kind of funny to read the title of this paper from 2006, which is just vector field design on surfaces. These were the first guys to do that. Now there's an entire field of computer graphics, but at the time this was it. It's kind of funny because it was the very first attempt to do this kind of thing, and from their perspective, which probably made sense given the graphics tools that were available, they put everything on mesh vertices, like scalars, vectors, everything. And so then they had to kind of figure out, like, what does it mean to interpolate a vector field inside of a triangle or do parallel transport? So you can do this kind of parallel transport construction where you flatten and then translate. But the problem is that in order to flatten, you kind of have to take the interior angles around the vertex and then kind of scale them to add up to 2 pi. And so they propose doing that in proportional fashion. So it's kind of an interesting idea. Like they kind of look at like what sector your vector lies in and then apply the proper scaling factor to that to translate. But as you can imagine, this is a complicated model. This is I think a paper since then kind of made life a lot easier. But anyway, if you like this kind of thing, you can page through this paper. Just recently, there's an interesting paper that actually works through defining connections and covariant derivatives in this setting. And it's an interesting read. I don't know how much this has been adopted really, but it's nice to know that like this is a thing you can do for vertex-based fields. But it's tricky. Okay, so that's our basic discussion of fields on meshes. One like little appendix to this story. This is actually the tip of the iceberg. There's actually other representations out there that are even more exotic. This is a really fun, weird space. So, for example, one thing that was proposed, I think this is sort of the topic of Henri Azencat's PhD thesis, and then got adopted in some little corners of graphics literature. Says the following: let's say that I have a vector field, then I can essentially, given a vector field and a scalar function on the surface, I can generate a new function on the surface, which is the directional derivative of that scalar function in that vector field direction. So in other words, like, I've got my field, whatever it is, and maybe it's varying, and then I've got some function on the same region. Then I kind of like take the derivative of that function in this direction here, derivative of that function in this direction there. That gives me a scalar at every point. So that leads to an operator. So for every vector field, if V is a vector field, then this operator dV, which inputs a function and then outputs another function, which is its directional derivative at each point in the V direction. Does that make sense? So what does that allow us to do? Well, it means that I can take a vector field and I can represent it not as a number per edge or per triangle or anything else, but rather as a matrix. This is like a linear operator that inputs functions and outputs the directional derivatives. And this is kind of useful in certain contexts. I mean, we just spent 5 lectures defining and working with this Laplace operator, which is kind of nice because it gives us this matrix where we can kind of convert a lot of geometry into linear algebra. They show that even more geometry can be converted into linear algebra if I use this kind of weird representation here. On the other hand, more basic operations with vector fields become really tricky. I mean, obviously the space of matrices is much larger than the space of vector fields. There's a lot of matrices that are not directional derivatives. So you kind of have to look at the space of, V by V matrices and then define a subspace of those that is some reasonable set of dVs. And so that's where things get tricky. But there's a whole series of papers by these authors in different subsets that show you how to define covariant derivatives of these fields and commutators and Lie derivatives and so on. It's a really creative little space, and it's got some interesting application. They show that for fluid simulation, this makes a lot of sense. Because here, in fluid simulation, you're often doing advection, which is really just making use of this kind of directional derivative construction. There are also even more exotic things out there. So for example, in computer graphics, it's very popular to take surfaces and subdivide them, have a very coarse mesh and then a rule for making a fine one out of it. You can ask a really fun question, which is if I have a vector field that is prescribed on the coarse mesh, can I come up with a subdivision rule that gives me a vector field on the fine one as I subdivide the underlying geometry? And then once you have that, can you do directional derivatives and exterior calculus and so on those objects using the coarse set of variables as a proxy? These are fun papers to read. There's still a lot of research to be done in this domain. Okay, so as always, I've talked too much, but maybe we'll stop there. We'll stop a little early for today. And the next time we will conclude our discussion of vector fields by going to the machine learning case and talking about some interesting vector field representations in that domain, and in particular defining an object called a continuous normalizing flow, which is a popular thing in probability domain. And then from there, we will finally be done with vector fields. Almost, because they also show up in transport theory. Sound good? All right, team. So with that, we'll conclude today's discussion, and I will see you on Thursday. Have fun with your homework, and I will see all of you in my office hours so that I'm not lonely. Okay, and now we've hit the stop button on these two devices precisely the same moment. 1, 2, 3...